questions. There was nothing due today. This is from a previous class, but I think it's always a good idea, look at the solution I do and then compare it to your solution and just make sure you're thinking about stuff right. Okay, so we have 3 1 kilogram books. Those are heavy books, but that doesn't matter. What? Yes, exactly. 3 1 kilogram books on a Ferris wheel, gives the radius of the Ferris wheel, gives the angular speed, and the direction is given by the arrow. And the Ferris wheel is speeding up at 8.5 radians per second squared. Okay, so what do we know so far? We know that the angular velocity is 2.5 radians per second this way. It's speeding up, so what direction is the angular acceleration? Same, yep. And that's 8.5 radians per second squared. And the radius is 6 meters. And so let's figure out the acceleration first, and then we'll go into Newton's second law, Newton's third law, and everything else. Okay, so the acceleration of the books, and we're not given different heights for them. If we were told thicknesses of the book or, the height of this whole thing, we could figure out the acceleration exactly of the middle book or whatever, but we're just assuming they're all, compared to 6 meters, you can imagine the height isn't very big. So we're just going to assume that radius to the books we care about is 6 meters. So the acceleration is the watermelon equation, alpha cross r plus omega cross quantity omega cross r. Alpha is equal to, this is a counterclockwise angular acceleration, so this is 0. Oh, and they give us a funky coordinate system. I almost missed that. So in this coordinate system, we have to think for a second, what direction does the positive y-axis point? X crossed with y needs to be equal to z. So the positive y-axis here has to come out of the page towards us. And so the right-hand rule says that, so I'm going to draw that on here. So our y-axis is coming out towards us like that. Oh, that's a y. And so from the right-hand rule, you can see that the angular acceleration and angular velocity are both in the positive y direction. So this is 0, 8.5, 0. And the angular velocity is 0, 2.50. And the r vector, that is in the negative z direction from the center of that circle. And so that is 0, 0, negative 6. So the acceleration is this. All right, well, so the acceleration of the books should be equal to negative 51 and 0, and then positive 37.5. And that's in this weird coordinate system. So now we're going to go to, what are we trying to find? At the position shown, what's the force vector the middle book applies to the top book? So we're trying to figure out a force on the top book. So let's just isolate the top book. And so we're going to assume that, well, there's a weight down of 1 times 9.81. And then we're going to assume that the middle book can apply a normal force, and then it also can apply a friction force. So we can just figure out this whole force vector. So we have a vector like this, and I'm just going to call that R. That R is the force on the top book by the middle book. Okay. And so Newton's second law says Rx, Ry, Rz plus 0, 0, negative 9.81 is equal to the mass times negative 51, 0, positive 37.5. And so R is negative 51, 0, and then 37.5 plus 9.81, 47.31. Yep.
So when you do that watermelon equation, you get an acceleration. Is that the acceleration of the box?
Yes.
So
that
to do like a relative acceleration to find the acceleration of the book, or no?
The book, and I'm assuming that the book and the box are moving as a rigid thing. That things aren't sliding around or anything. If it would have to be described differently if those were moving around inside the box. Any other questions? Is that all of it? Okay. So, I mean, I would say it's a pretty common like set of steps to follow to calculate the acceleration of the object first, and then go to Newton's laws and calculate forces. Like if we wanted to find it for the middle book now?
Yeah. Is it that question asking?
The question is asking what's the force applied to the top book by the middle book. So that's what we calculated.
So we don't need to wrap up the middle.
Nope.
Well, but the middle book might have like the opposite signs, right?
Exactly. So if we wanted to calculate now the forces on the middle book, given this, this is the force on the top by the middle. So then we could switch the signs, and that would be the force on the middle by the top. And then we could calculate the force on the middle by the bottom, and then we'd have everything we needed. Yeah, I'm going to do number, 13? Yeah, I'll get to, yeah, we can do as many of these as you want. It's almost spring break.
Are you going somewhere for spring break?
No, I'm grading. You know, the problem is like every school has different spring breaks and stuff. So like your kids don't have the same spring break that you have. Okay, so there's a cruise ship, and there's a carousel on it with a radius of 9.5 meters. observers on the ship see the carousel move in a way that's described. The passenger is at the dot. And then, according to, say, a video camera on the shore, something fixed to the ground, the ship's acceleration vector is -2, 2.5. Okay, so at the instant shown, what's the force vector applied to the passenger by the carousel? And this is a top-down view, so the when we get to Newton's laws, the direction of the weight force of the passenger is going to be into the page. All right. So we're going to have to use relative motion here because, so I'm going to think of this, the center of the carousel, as the ship. That's rigidly fixed to the ship. And this is the passenger. And we're going to calculate the acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the ship. That's the circular motion of the carousel, plus the acceleration of the ship relative to the ground. And this one is -2, 2.5. Since we're using cross product and stuff, I'll just extend that to a three-dimensional thing. And this one is the watermelon equation. So the acceleration of the passenger relative to the ship is alpha cross r plus omega cross quantity omega cross r. And this is uniform circular motion, the carousel. That means that alpha is 0. So this goes away. And omega, clockwise uniform circular motion we don't know what that is yet, so we have to figure that out. But we know that the passenger has come on now. Well, so let me write down R and then we'll figure out the, so R is equal to, this has a radius of 9.5 from the center of the circular motion. 2p is in the positive y direction. So this is 0, 9.5, 0. And to an observer on the ship, the 40-kilogram passenger moves with a speed of 16 meters per second. Okay, so we have to calculate omega. So you can take a minute to be with your thoughts, but now here's what's going on. So we have a circular motion to a passenger that's not moving relative to the center of this circular motion. We know that this passenger, it's going, oh no, not counterclockwise, it's going clockwise. So the velocity is going to be like this, and it's going to have a speed of 16 meters per second. Okay. So now we're going to use the velocity equation. So this is in the positive x direction, so 16, 0, 0 is equal to 0, 0, omega, the omega we're trying to find, crossed with 0, 9.5, 0. And so that tells us that, so 16 is equal to negative 9.5 omega. And so omega is equal to negative 1.684 radians per second. Yes?
Do you know it was 0 omega?
Because this motion is all in the xy plane. And so anything in the xy plane, omega and alpha are only z components.
We said that the speed in the x positive direction because passenger was at that point.
The passenger is at the top, and we're told that it's moving clockwise.
Okay, so it should be like tangential.
Yeah, so the velocity in circular motion is always tangent to the path. That's right. Any other questions?
Is there any scenario where this strategy does not work? Like you can't just divide the velocity by the radius? So if we were given this, like, fortunately, we were given this speed observed by somebody on the ship. It would get a lot messier if that was observed by somebody on the shore, fixed to the ground. And so I guess I try to just always go back to the handful of equations that I've given you, just as a way to think through it carefully, Also, it's a way to catch stuff if you make a mistake. Like if I would have gotten, so it says that it's clockwise. If I would have gotten a positive answer here, it would have been a trigger that something went wrong. I need to go back and rethink stuff, But definitely in this case, we could have done the same thing quicker by just saying 16 is equal to omega times r. Calculate omega and then think about the directions after. Any other questions so far? Yeah.
Is there an equation for omega? Can you write the equation for omega to find?
Yeah, this is, I'm using this equation for circular motion.
And you use the cross product, right?
Yep, and then I took the cross product and then I took the cross product, but you get 0 equals 0 for the y and z components. So I only took the x component. So you have one that says this, another one that says this. So those you can forget about, but the x equation is the one that we used. Any other questions? Yes.
So, like when we're dealing with cross products with variables in them, can we just like substitute them with like a 1 in the calculator and then plug them back in after?
Yeah. Yeah. As long as you know what components the variable is going to show up in, I think I do that. Yep. And then if you have a 89 or an Inspire, you can actually do it with variables, and it'll keep those in there for you.
With variables on the Inspire?
I've done it before. Within 3.5 minutes, I can remember how to do it. Any other questions?
After that, let's do 14.
Okay. This is, yeah, this is just to get our omega. And so now we're going back here. And we're using these two things. So our omega vector is equal to 0, 0, negative 1.684.
My computer knows it's spring break too. So we have that the acceleration of the passenger relative to the ship is equal to alpha cross r, and that goes away, plus 0, 0, negative 1.684 cross quantity 0, 0, negative 1.684 cross 0, 9.50. And so that is going to be 0, negative 26.940. That's meters per second squared. And now we have to calculate. So we want to go to Newton's second law, which means we need an acceleration in an inertial coordinate system. This is non-inertial. So now we're going to go acceleration of the passenger relative to the ground is equal to acceleration of the passenger relative to the ship plus acceleration of the ship relative to the ground. And so that's 0, negative 26.94, 0, plus the one that's given, negative 2, 2.50. And so that's negative 2, negative 21.440 meters per second squared. And that's an acceleration that we can use in Newton's second law. And so now we're trying to calculate the force vector applied to the passenger by the carousel. So free body diagram of the passenger looks like this. If so, from above, there's the passenger's shoulders, knees, back of their head. So this is the passenger from above. Okay. There's a weight force going in of the passenger has a mass of 40 kilograms. So 392.4. And then there is a force vector applied by the carousel. I'll call that R. And so Newton's second law says, so 0, 0, negative 392.4 plus Rx, Ry, Rz is equal to 40 times negative 2, negative 21.440. And so R is equal to,
Isn't 26.94 plus 2.5 24?
yep, thank you. 24.44. So this is negative 80, negative 977.6, and then positive 392.4. And so from like an engineering design perspective, these are the calculations you would do as you're trying to figure out how strong the supports need to be for, this carousel or whatever. You're like, okay, these are the kind of, this is the environment that it's going to have to live in. So we know it has to withstand this. We'll bump it up 50% or whatever to deal with, wear and tear over time or whatever. And then we know how thick the steel has to be and that kind of thing. Any questions? I don't think we've done this calculation yet, but we always we always assume that the shore is an inertial coordinate system. So like things are spinning around, the ship is accelerating, and we're like, we want to know what the acceleration would be relative to the ground, but the Earth is spinning, and so the Earth isn't really an inertial coordinate system either. So so what's the deal with that, So now we can do this calculation and figure out how non-inertial, so this is like an aside, how non-inertial is a coordinate system fixed to the surface of the Earth. So what we really want to calculate, so another way to ask this is how much is a point on the surface of the Earth accelerating? And the Earth is turning, and then it's also going around the sun, and then the sun is doing something, and then the galaxy is doing something, and whatever. But fortunately, each one of those effects diminishes. So I'm just going to deal with the rotation of the Earth. That's the biggest effect that we have to deal with. So this is just due to rotation about its axis. Okay, so let's think about it. So we have a sphere. This is the Earth. And it's rotating about a single axis. So I guess if up is north, it's rotating around the axis this direction. I think that's what you need for the sun to rise in the east. And because of the way the cross product works, the biggest accelerations due to the rotation of the Earth would be on the equator. So let's consider a point like this. That's a little bit of a funny thing. Like the people on the North and South Pole, they actually feel less acceleration due to this rotation than people on the equator.
If it would it be noticeable if you like?
Well, that's what we're going to calculate. We're going to see how small it is. It's small. But okay, so I'm going to put the origin here, and I'm going to do my coordinate system X, Y, Z. And then I don't remember the radius of the Earth, but it's large. What? So the axis of the axis of rotation is tilted slightly compared to the path of the Earth around the sun, but we're not thinking about the path of the Earth, so it doesn't matter. But yes, that is a good consideration. So radius of Earth, and so it is 6.371 times 10 to the 6 meters. 6.37 times 10 to the 6 meters. And so our R vector, the way I have my coordinate system drawn, is 6.37 times 10 to the 6, 0, 0. And now let's figure out our angular velocity in SI units. So this is in meters, so that's why we're using SI units. Well, we know that it does one full revolution every 24 hours, right? So we have one revolution. I'm going to just do this as a unit conversion. And we want to put this into SI units. One revolution is 2 pi radians. 24 hours, we don't need 24. 1 hour is 60 minutes. And 1 minute is 60 seconds. And so this angular velocity is 2 times pi divided by 24 divided by 60 divided by 60. And so you get 7.272 times 10 to the minus 5 radians per second. Okay, so we have a really tiny angular velocity, but we also have a really big radius. So let's do this calculation and see what we come out with. We're going to assume that there's no angular acceleration. It's basically a constant angular velocity. So the acceleration is equal to alpha cross r, and we're going to forget about this, plus, the way I have it drawn, this angular velocity is about the positive y-axis according to the right-hand rule. So we have 0, 7.27 times 10 to the minus 5, 0, crossed with 0, 7.27 times 10 to the minus 5, 0, crossed with 6.37 times 10 to the 6, and so the acceleration is about, so it's negative 0.03 3, 3, 7. Then these are zeros with the way I did it. Okay, so that is how far the Earth, a coordinate system on the surface of the Earth, is from being inertial. Okay, so as long as you're doing calculations that don't require a precision, as long as the precision, think of this precision is fine for you, then you can assume that Earth coordinate systems are inertial. If you need more precision than this for your calculation, then you have to take the Earth into account. Okay. Yes?
The radius would just reduce if you went all the way to the equator, right?
If you what?
If you went further north or south.
Yeah, just because the way the cross product works here, all that matters is the distance from the axis to the point. And so that distance to the surface is just getting smaller and smaller, and it reduces all the way to 0 if you're on those poles. Any other questions? Okay.
Do we have a assignment to do tonight, or?
No, I don't think so. These are all old problems. Okay, 14. So we've mostly been doing circular motion. We're mostly going to be doing stuff in the plane. So we're going to do a lot more circular motion than spherical motion. But this thing is moving in spherical motion. There's a radius of 2 meters. It has a constant angular acceleration vector. And at time 0, the angular velocity vector is this. But then it asks us a bunch of stuff at time 5 seconds. So we're not given, we're given the angular acceleration at 5 seconds because it's constant. But we're not given the angular velocity at 5 seconds. We're given it at a different time. So what we have to do is use the derivative relationship between angular acceleration and angular velocity and the differential equation approach to find the angular velocity as a function of time. So, okay, this is a definition. The angular acceleration is defined as the time derivative of the angular velocity. So I'm going to write, it like this. D omega dt is equal to 0 for -8, which we can think of as 3 separate equations. So we have, I'll just do them one by one here. So d omega x dt is equal to 0. So d omega x is equal to 0 dt. Integrate, and you get that omega x as a function of t is equal to c. And now we can use the boundary condition. We're given that when time is equal to 0, the angular velocity is 500. So what that says is c is equal to 5. And so omega x as a function of time is 5. So for all times, it's equal to 5. And then we'll go to the y component. So d omega y dt is equal to 4. So d omega y is equal to 4 dt. and we'll integrate. And omega y as a function of time is equal to 4t plus, I'll call it c again because we're already done with that first c. And the boundary condition says when time is equal to 0, omega y is equal to 0. So we have 4 times 0 plus c is equal to 0. So c is equal to 0. And so omega y component as a function of time is equal to 4t. Everyone with me on what I'm doing here? And then the last one, d omega z dt is equal to -8. So d omega z is equal to -8 dt. Integrate both sides, and you get that omega z as a function of time is equal to -8t plus a constant of integration. The boundary condition says when time is equal to 0, c is equal to, when time is equal to 0, omega z is equal to 0. So we have -8 times 0 plus c is equal to 0. So c is equal to 0. And so omega z as a function of time is equal to -8t. And so all together we have that omega vector as a function of time is equal to 5, 4t, -8t. And since this question just asks stuff at time equals 5, we can just plug in time and see what this is at time equals 5. This is 5, 20, -40 radians per second. Okay. And it gives us the R vector. And now we have alpha and we have omega at time equals 5. We have R at time equals 5. We have the angular velocity as a function of time. So now the velocity and the acceleration and the net force. Okay, so the velocity at time equals 5 is the omega vector crossed with the R vector. So that is 5, 20, -40 crossed with 0, 0, 2. And so that is 40, -10, 0.
And the radius doesn't change like when the time is 5.
Well, it just gives us the radius at time equals 5. It didn't give us the angular velocity at time equals 5. That's why we had to solve for that. And then the acceleration at time 5 is alpha cross R plus omega cross quantity omega cross R. So this is 0, 4, -8 crossed with 0, 0, 2. plus 5, 20, negative 40, cross with omega cross r, which we already did, is 40, negative 10, 0. So this one is 8, 0, 0. And this one is negative 400, negative 1600, negative 750. No, 850. 50. Negative 850. And so you get an acceleration of negative 392, negative 1600, negative 850. And that's in meters per second squared. And so what's the net force acting on this? Like, we don't know anything about what forces are acting on it. We don't know if it's cables or like a motor or whatever. But we do know that if it has this acceleration, we can multiply by the mass and figure out what the net force is. If you add up all the forces that we don't know, it's 5 kilograms. So F net is equal to 5 times the acceleration and you get negative 1,960 for X, negative 8,000 for Y, and negative 4,250 for Z. And this is in newtons. Any questions about that one? What was that, 14? Yeah, let me do 15 and then. Okay, so number 15. So we have this spinning disk that's moving along this path. And the center of the circle is C. And since, how do you know that the center of this disk is accelerating? From just glancing at what you're given in the problem. Exactly. The velocity isn't constant in time, so it has to be accelerating. Okay. And so I know that I'm going to go, and I know I want to do a calculation of the circular motion of this point O about C. So I'm going to right away write this as a problem of the acceleration of O relative to the ground is equal to the acceleration of O relative to C plus the acceleration of C relative to the ground. So I have to calculate both of these two. This is circular motion, so that's the watermelon equation. And this one is from the given velocity function. And this velocity is a function of x, not time, so we're going to have to use the chain rule here. The acceleration of the point O relative to C is alpha cross r plus omega cross quantity omega cross r. And it's uniform circular motion, so the alpha part goes away. Is the alpha part the tangential acceleration or the centripetal acceleration? That was 50-50 exactly. Tangential. Okay, so yeah, and if you think about the physics equation for centripetal acceleration, you can see the omega squared r right there. This is the vector form of the omega squared r. And the angular velocity is 15 radians per second. We can see it's moving clockwise. So omega is, I'm going to use, well, it doesn't say, it already gives us a vector, so we have to use whatever coordinate system that's using. But it makes sense to think that this would be in a coordinate system like that. It doesn't give us anything different to go on, and it gives us x and y components, so we know it's in the xy plane. So that means that omega is in the z direction, and it's 0, 0. Clockwise means negative. Computer. 15. And then the r vector goes from the center of that circle to O. The radius is 0.25. So this is negative 0.2500. So the acceleration of O relative to C, the center of the circle, is alpha cross r, that goes away, plus 0, 0, negative 15, crossed with the quantity 0, 0, negative 15, cross negative 0.2500, and that comes out to be 56.25 in the x, 0, 0. So now we have to calculate the acceleration of c relative to the ground for the relative motion. And we know that this is equal to the derivative of the velocity vector with respect to x times dx dt. dv dx is 0, 2. dx dt is the x component of the velocity vector there, 3. So this is 0, 6. And I'll write it in 3D like this. So the acceleration of O relative to the ground is 56.2500 plus 0.60. So 56.256. Any questions about that? And then the last thing, it asks for the net force. So we just have to multiply by the mass. So F net is equal to the mass of 10 grams or 0.01 kilograms times the acceleration so this is 0.5625 0.060 in newtons.
I do have a question.
Yeah.
What happens if for velocity, the x component of velocity does not derive like into just a constant? Or okay,
Yeah.
Here's my question. So
Yeah.
we're given v of x as a constant over something with x in it.
Mhm.
If our top variable or our top component also had x attached to it.
Yeah, that'd work fine. We've done in the chain rule stuff. We did a bunch of problems like that. So I'll erase this in a second. Don't write this down. But if so, say that you have v of x is equal to 2x squared, 3x squared. It still works just the same. The acceleration is equal to dv dx times dx dt. And so that is 4x, 6x, and now dx dt is just this.
So then our resulting acceleration would be dependent on what x is.
Exactly.
And then have to be given another value of x specifically to solve it.
Yeah, if you wanted a numerical answer, or you could just give the, well, yes, in this case, you would need to know, because we did circular motion at a single instant. So we would need to use that function somehow to represent the same instant. Yeah. Man, this thing doesn't like erasing, I've noticed.
So they wouldn't give you a new one, right?
You know what? They would give me a new one, but they don't have computers with styluses anymore. So I got to milk this as long as I can because I don't know what I would do without it. I'd have to get one of those crummy, I don't know, maybe they give me like an iPad or something. Yeah. Okay, number 8. So I really strongly recommend, if you don't, you probably don't have your homework sitting in front of you right now to do this, but the most useful way to use going through solutions like this is to go back and compare your work to this, you know, and it's a way to find places where like, oh, everything I did was right up until this, and I made this assumption or whatever. And it's just a way to find misunderstandings you have, you know. The other, like, you're thinking, oh, that's not the most useful thing is I can just write this down and turn it in. But that doesn't help you when the tests come very much, you know. So. Eight. Okay, so you have this thing moving along a path. What does that path look like?
Parabola.
It's a parabola, yeah. So remember that so parameterization of x and then some function is always the same thing as the function y equals whatever the y component is there. Okay, so so it's moving along a path like this. And this really has to tell us which way along the path it's moving, and I don't see that here. So let's say that it's going this direction. And okay, we have P, we have the speed is a constant 8. And what's the net force acting on the object when x is equal to 2? So we want F net at x equals 2. That means that all we need is the acceleration at x equals 2. So if we can simplify our derivative by making substitutions as we go, I guess we'll do that. These sometimes get a little ugly. So, all right, we have the parameterization. The first thing we need is a vector that is tangent to the path in the direction of motion. So I'm going to call that u. And that is going to be the derivative with respect to the parameter, whatever the parameter is. It doesn't have to be x or y or z. It could be arc length or whatever. And so this is 1, 2x. But we want to express the velocity vector as the product of the speed and a vector in the right direction. So we need a unit vector in this direction. One thing, so I said it didn't say in this problem whether it's going to the left or the right. We need to know that because this u vector is tangent to the path in the direction of that parameter increasing. So in this case, it's in the direction of x increasing, which means it's tangent to the path this way. Okay, so if the thing's going the other way, we have to multiply that by -1. Yep.
Vector u, you chain rule that, right? You just didn't show that.
No, I did not. I just took the derivative with respect to x because, so that's, if you have position parametrized, just take the derivative with respect to whatever your parameter is, and it gives you something tangent to the path in the direction of the parameter increasing.
How did you decide or figure out that it was moving to the right?
I didn't. I just said, stupid idiot question writer didn't give us that, so I got to put something in there.
So we're just assuming that moves right for the
Yeah. So if you're ever missing information for a problem, you might as well make it as simple as possible, you know. So we'll make it this way so we don't have to multiply by -1. Yes.
Would it like kind of like cancel itself out at the end or like kind of self-correct at the end?
Nope. Nope. Because we're going to take this unit vector that we get from this and multiply it by the speed, and that's going to be our velocity vector. And so that'll change kind of everything. Okay, so now a unit vector in this direction is, so we divide by the length. So this is 1 over the square root of 1 plus 4x squared. And then 2x over the square root of 1 plus 4x squared. And so therefore the velocity vector as a function of x is equal to the speed times that unit vector. So it's equal to 8 over that square root. And then 2x, 2x times 8. So 16x over 1 plus 4x squared. All right, so now we have the velocity vector, and now it's just a chain rule problem, except it's a messy one because we have this ugly derivative to do. But the acceleration as a function of x is dv dx times dx dt. Okay, so dv dx. So the first one isn't so horrendous, I guess. We have negative 1/2 times 8 times 1 plus 4x squared to the negative 3/2 times 8x. And so that is negative 32 over 1 plus 4x squared to the 3/2. The next one is going to be pretty ugly. So we have 16 over the square root of 1 plus 4x squared plus, well, minus 1/2 times 16x times 1 plus 4x squared to the negative 3/2 times 8x. So that is 16 over the square root thing minus 64x squared divided by 1 plus 4x squared to the 3/2. How sure am I that that derivative is right? I would say 26% sure. And now we can plug this stuff in. So we want dv dx evaluated at x equals 2. That's what the problem says. So we have negative 32 over 17 to the 3/2 power (17 to the 3/2 power). So negative 32 over 70.09. And then in the denominator, I think we have 0.228. So negative 0.457, 0.228. And then dx dt evaluated at x equals 2 is this thing, is this thing. So 8 over the square root of 17. So 1.94. And so the acceleration at x equals 2 is equal to negative 0.457, 0.228, all times 1.94. And that is negative 0.887, positive 0.442 meters per second squared. So that's the acceleration at x equals 2. Don't celebrate yet because we want the net force. Okay, well, that's kind of anticlimactic because that's easy. So the net force evaluated at x equals 2 is the mass of 3 times this acceleration. So negative 2.66, 1.33. And this is in newtons. Yes?
So when you did, plugging in the x equals 2 for dx/dt, what did you plug, x equals 2 into? Like what equation?
dx dt is the x component of the velocity. So I went up to the velocity here and plugged it into this.
Oh,
Can you look up some of the-
Yeah. Any other questions on that one?
Will we have question tests like this?
Yeah, possibly. I mean, I think it's long, you know. So in that sense, I mean, I try not to make test questions long like this. So I'd have to figure out a way. But I mean, really, I think this is a thought process that you should feel comfortable with, you know.
I have a question for when you're trying to do acceleration, like I just took the derivative of v.
Mhm.
So then, but you multiply by dx dt.
Yes, that's the chain rule thing.
Yeah,
So
because they're telling us that like it's about when x is 2 meters. Is that correct?
well, the reason you multiply is because acceleration isn't the x derivative of velocity. Acceleration is the time derivative of velocity. That's the definition. And so you need to use the chain rule here
Okay,
in order to take the derivative with respect to time, not x.
got it. Okay.
Okay. So anytime you have velocity expressed as a function of something that's not time, that should set off like danger bells, you know. You can't just take that derivative. You're going to have to, and you're going to end up doing some kind of chain rule thing. Any other questions? Okay. Happy spring break.